right, great. Thank you, Justin. So our next speaker is James O'Malley. He's an associate professor at the Department of Healthcare Policy at Harvard Medical School. He received his PhD in statistics from the University of Canterbury in New Zealand, and later that year was awarded the L.J. Cote Award for Excellence in Applied Statistics from Purdue University. His statistical interests include Bayesian statistics, hierarchical modeling, multivariate modeling, causal inference, and social network analysis. And just a sort of a side story of note, for those statisticians in the audience, you know that we have our annual JSM meeting each year in August, and was it last year? So each year at this rather large statistics meeting, there's a road race, and James won that particular road race last year. And he didn't know if he was happy or sad when people would approach him at JSM and say, you know, they recognize him as a runner, but nobody recognizes his work. Or they come up and say, James, what a great paper you wrote, or nice talk the other day. They all say, hey, you're the runner guy, aren't you? So anyway, James is also a tennis player, and he actually umpired some Davis Cup events, and will talk to us today about the tennis formula and how it might be used in professional tennis.
Yeah, so thanks to Mark and Scott for putting this conference together. The talk I'm going to give today, it's actually work that I started more than 10 years ago, a long time ago, and it's something that I've always kind of played around with a little bit here and there, but never really quite pushed through to maybe writing it up as a paper. And so for me, this conference is a wonderful opportunity. So just a brief outline of what I'm going to do in my talk. Firstly, I'm actually going to review the scoring in tennis. It's something that, unless you've played the game, you're probably not fully aware of it. Then I'll get to the so-called tennis formula and examine some of the mathematical properties associated with that, before moving on to other tennis-related formulas, and then looking at the applications of these formulas in tennis, how they can be used by players, by commentators, by coaches, and finally just consider some future work. Okay, so to begin with, the way tennis works is a player is either serving or receiving, and that contest lasts or is called a game. They'll play a service game, say, and the winner of that game is the person who reaches, on the one hand, as the first player to win 4 points, but that's only if they're 2 points ahead of the opposition player. If they get to, well, they start at 0, which is called love in tennis. If they win 1 point, they go to 15, 2 points to 30, 3 points to 40, and then if they win the 4th point, it's either game over, or if the other player already has won the 3 points, it's called deuce. And then they go into a situation where a player has to win by 2 points to win the game. And so you enter this situation where the game can go on and on and on and on. If one player wins the point, then the other player wins the point. Or a player wins 2 points in a row, but they started one behind, so they got to one ahead. Then the other player caught up again. And so that can actually, there's a large variability in how long a tennis game can actually go, which is, in my mind, one of the genius things about the scoring in tennis, because it could be that the winner of one of these very long games gets a real sort of benefit from that, and a game like that can have a major influence on a match. So, okay, so that's the scoring within a service game. Then the way tennis is structured is it's a competition of either best of 3 or best of 5 sets. So if it's best of 3 sets, then it's the first player to win 2 sets. If it's the best of 5 sets, it's the first player to win 3 sets. Each set is a competition of the first player to reach 6 games. However, if the players reach 5 games all, they then play on to 7 games. and if the players actually reach 6 games all, they play what's called a tiebreaker to decide the outcome of the set. The tiebreaker is a bit different from a service game in that instead of one player serving throughout the game, the serve rotates. One player begins serving, plays 1 point, then the next player plays the next 2 points, the first player plays another 2 points, and so on. And that continues until a player wins 7 points. However, if the score actually reaches 6 points all, then you reach another one of these sort of uncapped situations where a player has to win by 2 points to win that tiebreaker and the set. And so the tiebreaker can become quite a long thing too. The final score could be 20 points to 18 even, or even more extreme. Okay. Right, so now I'm going to introduce what's called the tennis formula. This particular formula has this infamous title because it was the first formula I'd actually worked out to do with tennis. Over the human existence, it may or may not have as much acclaim as E equals MC squared, but we'll see. Anyway, what I devised is I said, assume that the player serving has a fixed probability P of winning a single point on serve. So that's the player serves the point, they've got probability of P of winning that particular point. And that remains static throughout the game, and the points are played independently. So the fact that you won or lost the first point has no bearing on the outcome in the second point. Then this formula here tells you the probability that you will win the service game. The first expression, or the first line of the formula, has actually got it expanded out through the various ways in which the service game can be won. You can win 4 points straight, in which case you have P raised to the power 4. Okay, so that's first scenario is 4 points straight. The second scenario is you lose 1 point on the way to winning the service game. Third scenario, you lose 2 points. And you see there's 10 different ways in which that can happen because there's different orderings of winning and losing the point. And the final situation is you get to deuce, and these 20 times p cubed times 1 minus p cubed are all the different, well, is the probability of getting to deuce basically. And then this term here is the infinite sum that occurs to deal with the deuce advantage situation and the fact that can go on and on. So it's actually a geometric series. And so the probability of winning the game is the sum of all of those, and I can actually do some algebra and reduce that to a simpler looking expression, but it's a more disguised expression. It's not as intuitive as the top formula. Well, I can plot this function, the tennis formula, as a function of the probability P of winning a single point, and then on the vertical axis the probability of winning the game. And understandably, if you've got 0 probability of winning a point, you have 0 probability of winning the game. And the same at the other extreme, probability 1 of winning the point. Well, there's no way you can lose the game. But what's interesting is just to look at the curvature of this function as your probability of winning a single service point increases. Right at 0.5, you have a 0.5 chance of winning the game. So that's like the even contest. Both players have an equal chance of winning every point. So it makes sense. You'd have 50% chance of winning the game. Then if you look at the derivative function of the tennis formula, you see that it actually obtains its maximum value at 0.5. And so that's if you were to, say, go from a 0.5 chance of winning a point up to a 0.51 chance of winning the point, then you would have quite a big increase in your chance of winning the game relative, say, to if you were already at a 0.8 chance of winning the point, and then figuring out what improving your serve up to a 0.81 chance would have of winning the game. So just in terms of little mathematical curiosities, you can actually also work out the integral function of this tennis formula, and that's shown on the bottom here. And of course, the integral averaging all the way from 0 to 1 probability will equal 0.5. that's interpretive as saying, imagine that the performance of players was uniform, so their point probabilities were uniformly distributed all the way from 0 to 1, and you chose a player at random to serve for you, if you liked, then you would ultimately, again, have a 50% chance of winning that game, averaging over all types of players. Okay, so more or less, well, I have the algebraic expressions for the derivative and integral functions. I just note that the tennis formula is asymmetric. The receiving formula, if you like, would just be 1 minus the probability of winning the game on serve. And of course it's monotone increasing. Okay, so that was my initial work. I did that and I called that the tennis formula. And I'm going to get to uses, like applications of the tennis formula soon. But I just wanted to consider some other things we might work out about the tennis game under various statistical assumptions. And so one is, well, the probability of winning the tiebreaker, or the probability of winning a single set, or in fact the whole match. Then again, we might be interested in working out the probability that a player makes a comeback, recovers from a breakdown to win the final set, say. Just as a general approach to working out these formulas, they can all be derived using a kind of dynamic programming or tree diagram approach, where you consider just the sequences of points in a game and what happens if the player wins this point versus that other point, and then you go on to the next situation. Okay, so let's consider the probability of winning a tiebreaker. So I'm now going to introduce a second probability, and I'm going to call this Q, and that's going to be the probability that the opponent of our player wins a point on their serve. So think of 1 minus Q as the probability that you win a point when you're receiving serve. Okay. And then I have 3 plots here dealing with 3 different situations. The first plot is when your receiving probability is fixed at 0.5. So when you're receiving serve, you have a 50% chance of winning a single point. And then the plot is of a function of winning the probability of winning a tiebreaker as a function of the probability P that you win a service point. So again, as you go from 0 up to 1, your probability of winning the tiebreaker increases, and it reaches the 0.5 mark as you would expect at 0.5. So that's scenario number 1. Scenario number 2 is where we actually make P, your probability of winning a service point, equal 1 minus Q, which is your probability of winning a receiving point. So it's like saying throughout the tiebreaker you have the same probability of winning each individual point. Then what is the probability that you win the tiebreaker? Now we see another one of these kind of S-shaped curves, but this curve's actually steeper than the one used for winning a game on serve, where you're just serving all the points. And that makes intuitive sense, because a game is basically a contest to 4 points, whereas the tiebreaker is a contest up to 7 points, and both of them have this ongoing situation if they either get to the deuce or get to the 6-all scenario. So the tiebreaker is a contest over a longer or a greater number of points. So by the law of averages, if your probability is above 0.5, then because you're playing a greater number of points, your chance of winning the tiebreaker is going to be greater than your chance of, say, holding a service game. So we have a sharper incline there. Then the third one is to say, well, let's imagine that you're just a little bit better than your opponent. So your probability of winning a service point is greater than 0.02. It was 0.02 greater than your opponent's probability of winning a point on their serve. And then as a function of this probability P of winning a service point all the way from 0 to 1, we work out the probability that you win the tiebreaker. Now this comes out to be a bathtub-shaped curve, which is intuitively obvious in a way, because if you take your probability P to be 0.02, then your opponent must have probability 0 of winning a point on their serve. So they in fact will have no chance of ever winning the tiebreaker because they could never get 2 points ahead of where you are. They would lose all the points on their serve. So basically as soon as you won a point on your serve, you would win the tiebreaker. And then it actually levels down and has its lowest point close to 0.5, where your odds are about 0.6 of winning the tiebreaker. Remembering you've got a 2% chance higher of winning a single point on your serve than your opponent. And then the reverse thing happens as your probability of winning serve goes up to 0.1 and your opponent to 0.98. In this situation, where it's highly likely the score would get to 6-all and there'd be a very long sequence of points won on serve until you finally won your opponent's or won a point off your opponent's serve and thus won the tiebreaker. Okay. So I just have made this point that these longer contests will actually favour the better player more and more. So it sort of, if you like, gives the better player more opportunity to recover from a mistake in the early part of the contest. Here I've actually given the same analysis as I did for the tiebreaker, but for the probability of winning a match. And this was for a best-of-3 set match. And so here you can see that S-shaped curves are actually steeper still, because going all the way from your probability of winning a single point through the probability of winning the entire match, that's a very large contest. And so if you're just a little bit better than your opponent, so just a little bit above the 0.5 mark, your odds of winning the whole match are quite a lot bigger than 50%. The most interesting plot, perhaps, is the one where you say you begin off by being just a little bit better than your opponent. So again, I've used 2% or 0.02 probability point differential on their serves. Then again, you've got a bit of a bathtub-shaped curve where you have to win if your probability is 0.02 and your opponent's is 0, obviously, and the same if your probability is 1 and your opponent is 0.98. But then over the middle range, it's interesting that your probability comes down to around about 0.2, but then it actually goes up a little bit when you're in the range of, say, your probability being 0.5 and your opponent's being 0.48. So close to this sort of 50% point-winning chance. I don't have a strong intuition as to what's happening here. I think it's just the competing behaviour of the extreme cases where you have to win because your opponent has no chance of winning a point on their serve or no chance of winning a point on your serve, and then there being greater variability in this middle area here close to 0.5, which kind of gives you more chance to recover from an early point lost or an early breaker serve or something. So that was an interesting little curve that I've found out there. And then finally, my final plot of this nature is to compare your odds of winning a best-of-3 set versus a best-of-5 set match. And so, again, like the best-of-5 set match will in theory give the better player more chance because it's a longer contest. And that is what we observe here. So again, your probability of winning a point is down here. And this is for the scenario where your probability P is equal to 1 minus Q. So your probability of winning a point on serve equals your probability of winning a receiving point. So it's like just repeated experiment with the same probability. Then if you have 0 probability of winning a point, then 0 probability of winning the match under either scenario, so obviously that's 0. And your difference in the probability of winning the match between 5 and over a 5 and a 3 set contest is 0 for most of the scenarios, and it's only around about the 0.5 area that you actually will see some difference there. And as one would expect, your relative chance is lower if you're a little bit, your performance is a little bit worse than your opponent. So say you have a 0.49 and your opponent therefore has a 0.51 chance of winning an individual point, then you're going to actually do better in a 3-set match than a 5-set match because it's a shorter contest. But if you're a little bit bigger than your opponent, you'll do better over a 5-set match than a 3-set match, because again it's a longer contest. And out close to the extremes, it's like you're so likely to win the match that under either circumstance there's no difference basically in the probabilities. Okay, so that was just sort of maybe doing some more theoretical type investigation about tennis. I now wanted to make some comparison to actual empirical data to see if this formula is going to be accurate. It's important to recall that the formula is based on very simplistic assumptions. So these independence between points, and the probability stays identical all the way through the course of the match. So I obtained some data from this year's Wimbledon tennis tournament, and I compared the empirical game-winning percentages to the actual predictions based on the tennis formula. And so here's a plot that I've made. Basically, for every match, I determined the probability or the proportion of points that were won on serve, and from that predicted the proportion or the proportion of games that should therefore be won on serve, and compared that to the actual observed proportion of games. So on the vertical axis we've got the observed proportion of games won by the server. On the horizontal axis, the predicted proportion of games won by the server. And you can see the variation in the data, but basically there is just a straight regression line from, I've only plotted it from 0.5 up to 1,1 because there are no situations where the server won less than 50% of the points. So that gives you an indication that, maybe the way the points go in a tennis game is close to these assumptions. Maybe they're reasonable. I did a very simplistic test and got an insignificant difference there. But if you actually dig deeper in the data, then you get a little bit less satisfied about the legitimacy of these assumptions. The scenario I looked at was breakpoints. So if the assumption that the probability of winning the point really was static throughout the entire game, then your probability of saving a breakpoint should equal your probability of winning a point at any other stage of the service game. In these data, I had over 3,000 points. I only had the quarterfinal data onwards in the men's singles. And so on breakpoints, there were 208 breakpoint opportunities, of which the server managed to save 118 of them. So it was like 55%. Then in the other parts of the service game, there were 2,101 points out of 3,156 points that were won by the server. So there you had a probability of 2/3 basically. And a simplistic test that's not taking account of all of the forms of clustering in these data would actually tell you that, well, there's a significant difference. So it seems like on these data, the servers were doing worse on break points than they were expected to. So that would be taken as evidence, perhaps, that the constancy of the probability of winning a point is not a valid assumption. I would actually point out I had previously done some analyses on data from the late 1980s, and on that data, again, there was a bit of a difference between break points and other points of the service game, but the difference was the other way around. In that particular, or those years, the servers actually did better on the break points than expected. So I think there's obviously one needs to look at a lot more data before maybe making a firm conclusion here, and maybe the effect changes depending on other circumstances. But at least the tennis formula gives you a way, or sort of like a control, to do such tests. Okay, so then what applications of the tennis formula might there be? Well, one is the players could potentially use it to work out where they would gain the most benefit if they were able to improve their games in certain ways. So is it better for them to work on their service game or their receiving game? It could be used like right before a match even by players in the same way, but by just looking at the data they have in previous matches against a particular opponent. And it could be used, quite importantly, by commentary teams to make their commentary of a tennis match more interesting to viewers. And finally, I just want to touch on one other application, which would be determining the effect of a rule change. So I'll try and go through these quite quickly, but basically my idea is like players could analyse their data either against all opponents if they were like in training and wanting to have really like make a major improvement to their game, or if they were playing like right before a match against a particular opponent to look at their head-to-head data against that opponent. And it could be done in the following way. This is a very simplistic, perhaps unrealistic example, but imagine the player currently has a 0.65 chance against all opponents of winning a point on serve, and a 0.37 chance against all opponents of winning a receiving point. So they're kind of an above average player compared to their competitors. And so it would mean their probability under those conditions of winning a 3-set match is about 0.6. So imagine for the same amount of effort or in their time available, they could improve their service point winning by 1.1%, but they could only improve their receiving point winning chance by 1%. And in that case, it would actually work out more beneficial to focus their efforts on improving their serve. They would increase their chance of winning the game by a little bit more than if they worked on their return. But notice this condition kind of advantaged the service because it said you could improve it by a little bit more. If I actually had made this 1%, so the same as the receiving percent, then they would actually be better off working on their return because their service probability is further than 0.5, where you get the greatest amount of change. So if the players were able to kind of work out these expectations of how much they can improve their point-winning chance by, then they could work out what they're better off doing. And they could do the same sort of thing just before like playing a particular opponent. They could work out like, how do I want to warm up? Do I really want to focus on my serve or receive, or kind of do things like that. Then one of my pet peeves when I'm watching tennis on television is how often I hear the commentators say, well, if player A, who might happen to have a wonderful reputation, breaks serve now, the match is as good as over. I really object to that statement because one of the great things about tennis is the only point in the entire match that actually matters is the last one. Whoever wins the last point wins the match. And the contest goes on to that very last point. There's no time clock that runs out or anything else. And comebacks happen all the time. And so I wanted to sort of, figure out some probabilities of players making comebacks. And I don't know if there's anyone here from the media, but if they could have a word to maybe the tennis people doing commentaries, that maybe they could have a little line about expected chance of the two players winning a match from a certain situation. I have some situations here. So imagine that a player is down a break of serve, and these are all the various scores that a player can be down a break of serve. And in this case, I'm assuming it's the final set of the match. So in the first case, imagine the player has a 62% chance of winning a point on serve, but their opponent is a little bit better. They're at 67% chance. Then, if they're down 4-5, so that means their opponent is winning 5-4 and their opponent is about to serve, they have about a 14% chance of recovering to win the set and the match. If they actually were the better player, their odds are actually up to about 22%. If the players were actually equal ability, equal at 0.645, then they're in between, about 17%. And the final scenario is I have what I call the tossing the coin scenario. If they actually stopped the match, stopped playing tennis, and flipped a coin instead of playing the tennis points to win the match, so assuming it's 50% chance, they'd have a 25% chance of recovering. So quite a range of probabilities depending on the relative merits of the players. And then notice that as the score is actually further away from the end of the set, these probabilities decay at different rates. Obviously here 2-5 down, you may only be down one service break, but you've got to win your own serve, break serve, and win your own serve again to get back even. Then, as you go to the scenarios that are further from the end of the set, so you actually can afford to lose a game, another game, and still come back to win, all the odds will go up, because again you've got more opportunities to make that comeback. And obviously in this case, where you're the better player, you get to have quite a high chance. But anyway, so my idea is the tennis commentator, well, on the scoreboard, on the television screen, as well as the score, they could have these little percentages for each player, what's their chance of recovering to win the match from this point, and maybe under different assumptions, like over their lifetime probability of winning point on serve and return against this opponent, or maybe within the context of the actual match, or maybe under the tossing the coin scenario. But at least it would be better than just sort of saying, well, this player, if they hold serve now, is going to win the match, when the odds are not trivial that that will happen. My final little application was just looking in 1999, there was this proposal to do away with the deuce advantage situation and just replace it with, if the score gets to deuce, the winner of the next point will win the game. And so that would actually be changing the tennis formula. This would be the new formula, so just this last term has changed. Two top players at the time had differing viewpoints. Pete Sampras didn't like the change. Andre Agassi liked the idea of the change. I've got some approximate data of their serving and returning point-winning probabilities for that year. Sampras the better server, Agassi the better returner, and then worked out the probability that they win a 3-set match under the new and the old, or the current, scoring rule for a game of tennis, and then their differentials. Both players are better than like the bulk of their opponents, and so the effect of the rule change is to compress and make the contest a bit shorter, so they actually both lose out. Agassi loses out by a bigger amount, interestingly, especially since he was in favour of the change. So I think you've got to say Sampras maybe is the better probabilist. Okay, so I'll more or less end there. There is a lot more work to do to consider like various other models than the independence model I considered. Thank you.
Okay, we're going to have a 15-minute break. There should be snacks and beverages outside to help yourself. We'll reconvene at 11:15.